Right now, as you watch this, the sun can dump more energy in minutes than humanity uses in years, and a single big flare can hit Earth with radiation in about 8 minutes. What if I told you the real danger isn't the flash you see? It's the invisible second punch that can arrive hours to days later. Stay with me because by the end of this video, you'll know what a massive solar flare means for your phone, your GPS, your power grid, and whether tonight's sky becomes an aurora show or a global headache. This sounds impossible until you realize we live inside a star's blast radius. One outburst on the sun can disrupt HF radio used by aircraft on polar routes. It can stir up the upper atmosphere and mess with GPS accuracy. It can increase satellite drag so orbit predictions get sloppy. And in the worst cases, it can drive electric currents through long power lines like the planet just became part of the circuit. Here's why space weather scientists get careful. Fast. A flare is often just the opening act. The question that matters is simple but brutal. Did that flare launch a coronal mass ejection, a CME, toward Earth? Or was it mostly a flash? And how can you tell before the impact arrives? Let's ground this in normal science. A solar flare is a sudden release of energy when twisted magnetic fields in the sun's atmosphere reconnect, like a stretched rubber band snapping, except the rubber band is made of magnetism and plasma. That reconnection dumps energy into radiation, X-rays, and extreme ultraviolet. Space weather centers classify flares by strength, C, M, and the biggest X-class, based on X-ray intensity. A CME is different. It's not just light, it's a physical cloud, a giant bubble of plasma and magnetic field launched into space. A flare can happen without a CME. A CME can happen with a smaller flare. And that difference is everything. This is where things get strange. The sun can hit Earth in 3 different ways. 3 arrivals, 3 kinds of impact. And this is how you stop getting fooled by headlines. First arrival. Light speed radiation. X-rays and extreme UV reach Earth in about 8 minutes. That can cause near-immediate radio blackouts on the sunlit side by ionizing the upper atmosphere and messing with the layers that bounce radio signals. Second arrival, solar energetic particles. Fast protons can arrive in tens of minutes to hours depending on the event. These matter for astronauts, for satellites, and for high-latitude airline routes, because radiation levels can rise where Earth's magnetic shielding is less protective. Third arrival, the big one, the CME. That plasma cloud usually takes about 1 to 3 days to travel from the sun to Earth, sometimes faster, sometimes slower. When it arrives, it doesn't burn the atmosphere like a movie. It pushes and compresses Earth's magnetic field and injects energy into our magnetosphere like someone shaking a giant invisible snow globe around the planet. And that's why massive flare headlines are tricky. The flare looks dramatic, but the CME decides whether we get a beautiful aurora night or operational chaos. Quick pause. Subscribe if you want real space weather explained without panic. What I'm about to reveal is the exact checklist scientists use to judge whether a flare is mostly a headline or the start of a storm that can actually disrupt Earth. And the last step, the one almost nobody talks about, is the difference between pretty auroras and serious trouble. Stay with me here. Now let's do the detective story, because we learned these lessons the hard way. Back in 1859, astronomer Richard Carrington observed a powerful flare, and shortly after, telegraph systems malfunctioned, one of the most famous space weather events on record. In 1989, a geomagnetic storm contributed to the Quebec power blackout, a modern reminder that you can live far from space and still get hit by space. Fast forward to the mid-2020s, moving into the 2026 era, we don't just notice the sun anymore. We monitor it continuously. X-ray sensors track flare intensity. Solar telescopes image active regions. Coronagraphs watch for CMEs leaving the sun. And upstream spacecraft sample the solar wind before it reaches Earth, giving us critical last-minute warnings. Scientists around the world follow the same sequence when a big flare erupts. Clue 1, the flare's X-ray spike tells you it's real, and how intense the radiation hit is right now. Clue 2, coronagraph images tell you if a CME actually launched. If you see a big expanding halo around the sun in coronagraph imagery, that can mean the CME is coming toward us because we're looking down the barrel of the eruption. Clue 3, models estimate arrival time, hours a day, maybe 2. That's when the tension builds because the biggest uncertainty isn't only speed or direction, it's the magnetic orientation. And this is the cliffhanger. Even a fast CME can be mostly harmless if its magnetic field doesn't connect with Earth's. Here's the reveal. The 3 factors that decide what a massive flare and its storm actually mean for Earth. Think of it like a storm hitting a house. Wind speed matters, but the angle and the open windows decide the damage. Factor 3. How big was the flare? Big flares mean strong radiation now. Radio can drop out on the daylight side, especially HF. You might not notice this at home, but aviation and certain communication systems absolutely do. Factor 2. Did a CME launch, and how fast is it? The CME is the moving wall of plasma. Faster CMEs tend to compress Earth's magnetic field harder and can drive stronger geomagnetic storms, especially if the internal magnetic field is aligned the wrong way. Factor 1. The CME's magnetic orientation, the BES problem. This is the last step most headlines skip. If the CME's magnetic field
points southward when it hits Earth, it couples more efficiently with Earth's northward field, like 2 puzzle pieces clicking together. That opens the door for energy to pour into the magnetosphere. If it points northward, the coupling can be weaker. Same CME speed, totally different outcome. And here's the frustrating part. We often can't confirm that orientation until the solar wind actually arrives at near-Earth monitors. So experts sound cautious for a reason. The most decisive variable may be unknown until the last moment. So what does this mean for you? If the storm couples strongly, auroras can spill far from the poles. Satellites may switch to protective modes. Some navigation errors can rise as the ionosphere becomes turbulent. Airlines may reroute polar flights during elevated radiation periods. And power operators may prepare for geomagnetically induced currents, currents that can flow in long transmission lines and stress grid equipment. But if the CME is weak, misses Earth, or arrives with a northward magnetic orientation, you might see nothing. That's why one massive flare can lead to an incredible aurora night, and another can fizzle into a non-event for most people. And that raises a new question. If we're watching the sun better than ever, why can't we forecast the most important part, magnetic orientation, earlier? Just when you think you understand, here comes the second twist. Solar storms can stack, merge, and fake you out. Sometimes multiple CMEs launch close together. One can catch another. Shocks can merge. Magnetic structures can change en route. That's when forecasts can swing fast, from minor storm to surprise major, because the storm that arrives at Earth isn't identical to the storm that left the sun. There's real debate about the best path forward. Some researchers push for more spacecraft positioned off the Sun-Earth line so we can see CMEs in 3D, not like a flat shadow. Others push for better physics-based models and machine learning tools trained on decades of solar behavior. In practice, the future is probably all of it at once. More viewpoints, better models, and faster, more reliable warning pipelines. So even in the 2026 era, the most honest answer is we're better than ever at seeing storms coming. But the sun still has a talent for ambiguity. I genuinely want to know what you think. When a massive flare erupts, what worries you most? A. Power grid disturbances. B. Satellites and GPS disruptions. C. Radiation risk for flights and astronauts. Comment A, B, or C and tell me where you live because latitude changes everything. I read the comments and I'll pin the most insightful one. Because this isn't just a space nerd problem. Space weather is one of the few natural hazards that can touch multiple systems at once. Communication, navigation, power, and space infrastructure. Modern life is synchronized by satellites and precision timing. Even if your lights don't flicker, a storm can still ripple through systems you rely on. The good news is we're not helpless. We have warning systems, forecasting centers, and operators who train for this. Every storm improves the models. Every near miss teaches grid operators and satellite teams how to reduce risk.
The goal isn't panic, it's resilience. Hardening infrastructure, improving satellite autonomy, improving forecasts, and building smarter response plans. But this isn't the only solar event that can change everything. Next, we'll break down what a modern Carrington-level storm could do, how auroras really work, and what satellites do to survive space weather. Subscribe, because the sun is active, and this story keeps evolving. Thanks for watching. The sun powers life, and occasionally reminds us it's a star. Stay curious, stay prepared, and see you in the next one.